Oh, welcome guys. So today we're going to look at the pressure systems. It's been a while. It's good to be back. So I hope you've been fine. So let's continue with the pressure systems. So what are these pressure systems? So pressure systems are basically systems that are generated due to pressure disparities, pressure differences. So we have the major types are two. We have what you call them, the high pressure system, high pressure. You know, you have heard of that, high pressure system. Then we also have the low pressure system. Low pressure, both of them are systems. So the high pressure systems, we also call them anticyclones, also known as anticyclones. The low pressure systems, on the other hand, we also call them the cyclones. In some other people also do call the low pressure systems. They can also be called the depressions. But I tend to use just cyclones and anticyclones or high or low pressure systems. So this is as simple as it gets. And then we have one that is neither of the two. It's neither high or low. So which one? We call it a cold. So we have high pressure system, low pressure system, and then we have a cold. So a cold is a formation, is a place where we don't have either high pressure system or a low pressure system. So then let's look at just to mention, we also have what we call troughs and ridges. So as a start, I can just mention them. So a ridge is related to the high pressure system, and a trough is related to the low pressure system. So a trough, you can get some places, some people call it a trough, a low pressure trough, whilst some other people say a high. You can either say a low pressure trough or just a trough, or a high pressure ridge. So if I just say a ridge, by the fact that I'm saying it's a ridge, you know that it's a high pressure ridge. So let me define for you. So ordinarily, I know you have seen isobars that way. Then there's a protrusion because you have a depression here, and some cases it might be L. So what did he say L means? Obviously low pressure system. Good. So because the L stands for the low pressure system, then we look at a low pressure system. So you can see there's a finger-like protrusion here, and this is what we call a trough. So this is what we call a trough. Remember, these are isobars all around, and then this is the lowest pressure area, low relative to the surrounding. So that's what determines whether it's a high or a low. It's majorly because of the relativity in the way isobars are either dropping or increasing. So this is a low pressure trough. Then we have what we call a high pressure. You can have a high pressure, and then we notice that in the high pressure, the isobars are usually far much spaced apart. We'll see why. Then there's a finger-like protrusion here, so this is what we call a ridge. Well, now we're done with pressure systems. Wunderbar. Okay, thank you for watching. Actually, we are not done with pressure systems. This was just the introduction. So We want to see each one of them as a unit. So we'll first look at high pressure. Which one do you want us to look at? High pressure or low pressure? Which one? Which one? Okay, let me guess. Let me guess. Okay, let's look at high pressure. High pressure systems first. Okay. Okay. So now we're going to look at the high pressure systems. So which are these high pressure systems? So if you can look at the laptop, if you can just have a glance at the laptop, you can see what I call the different types of cells. So just get a picture of that. We have the first one on the equator. We have a low pressure region around 0 degrees. Why is it the case? Because the temperature there is high, and then that temperature causes air to rise, and then as it gets to the atmosphere, there is a divergence in the upper layers of the atmosphere. So it diverges, and then one goes south, the other one goes north, forming the Hadley cells or the Hadley cells, depending on which school you went to. So you have those two different types of cells, and then on the other, from around 30 degrees north to 60 degrees north or south, we have what we call the Ferrel cell, and then we have the polar cells. So those are the types of cells that we have in the global atmospheric circulation. So we'll use that in our analysis of our pressure systems. Now that you have seen that, I think now you know. Sorry. Having said that, then now we can look at the high pressure systems. So we can look at, because of the different atmospheric circulations on the globe, we have two places where we have high pressure. So what the major difference between a high pressure system and a low pressure system is how the air is moving, vertically and on the ground or in the upper layers of the atmosphere. So for a low pressure system, air converges at the surface. This is the surface. Air converges at the surface, and then it ascends. We'll see why it is doing so, and then it diverges. It diverges on the outer layer, on the upper layers of the atmosphere. But on the high pressure system, the opposite is the case, because when you have a ground that you're experiencing high pressure, what happens? Air moves from high to low. So what happens is the air will diverge on the surface. It will diverge on the surface. As the air is diverging, it will cause a subsidence. So there's a subsidence on the high pressure region, and then on the upper layers you get what we call convergence. So I want you to look at the two there. This is high, this is low, and you ask yourself, why is it that here air is leaving and there's air coming in and there's air leaving? So why should we have a net loss? Because there has to be something that has lost. So either kitu imeongezwa ama kitu imetolewa. So ask yourself, because here, for example, you have high pressure, but you're saying air has moved away, but here you're saying air has gone back. So ordinarily, I've given you something and you've given me back. So there should be an increase in pressure. They should not be. But this is the case, because here you are on the ground. This is on the ground. So the rate at which this air is leaving the ground is slower, because on the ground you have buildings, you have terrains, you have areas, friction and all those. So at the lower layers it is gradual, than at the upper layers you don't have any resistance, so the air just keeps on coming swiftly. But as it comes, it gets to a point where it doesn't flow freely. So like water, if you block the waterway, what happens is that it creates a dam, it creates something. Yeah, it creates a dam, so it clogs. So there is a dam that is created vertically here, causing pressure down here. Same way here, air is leaving fast, then it is being replaced. But here, air is coming in fast and it's leaving. So here you have high, here you have low. So that's the major difference. So now that's the cause. So high pressure systems are caused when the air at or on a point is heavier than the other. So if you have a column up here, so there, so if this maybe air here is heavier than the surrounding, here air is light. So here you have the pressure in this region is extremely high. Why is it high? Because of this. Because there is air coming down and air. So there is this type of flow of the air. But what causes that flow? That's where we're going now. What causes that flow? Because air has to come from somewhere ideally. Because here we have a lot of air, here we don't. So how does air increase? You have said it converts there and then it comes back. But what triggers this action? Okay, what triggers this action? Of air moving, of air converging at the top, descending, and then diverging at the bottom. So we have two types of ways that cause this movement. So you have two types of reasons, two types of ways that lead to that. And the two types of formation gives rise to the two types of high pressure systems. So depending on the formation, it leads to two types of high pressure systems. Sorry, it leads to two types of high pressure systems. So which are these two types of high pressure systems? So one of them is the permanent. One of them is a permanent warm anticyclone. This is a permanent warm anticyclone. You can feel it for yourself, cyclone. And the other one, obviously, when you have something that is warm, obviously you should expect the negative of it. So the other one is the cold anticyclone. And remember, anticyclone, when you say anticyclone, we don't mean the cyclone as we hear it. Anticyclone is the opposite of cyclone, definitely. So cyclone is low pressure, anticyclone is high pressure. So you can also say permanent warm high pressure system, or cold low pressure system, or cold anticyclone. Good. So having said that, then now we want to look at the two of them concurrently, so that we demystify how we can relate to the two. Okay, so now we are on permanent warm anticyclone and cold anticyclone. So all of these are high pressure system, and there's another one that we will look at it's called another one, a form of this. It's called temporary anticyclone. So don't worry about that. So now we have the two. So how are they formed? So this is the permanent one. Both of them, amazingly, formed under one principle, that due to excess air in the high altitude. So due to excess air at high altitude areas. Same to this one. Due to excess air at high altitudes areas. So you can say high altitude areas are in upper levels of the atmosphere. Okay. So for this one, it occurs between, remember the three cells that we talked about on the global atmospheric circulation. So the three cells we had there, the one at the near the equator, it was called, let me just draw it for viewers who are just joining us. So we had one here, another one there, and then another one there. So these two, this was the Hadley cell, and this was the Ferrel cell. So you'll notice that on the Hadley cell, what am I drawing? So near the equator, air goes up, that comes down, goes that way. And on the Ferrel cell, it comes that way, and then goes up. So you can see here, we have a suspect. What do we have here? Excess air, because air is coming together. So we have excess air at high altitude areas. So this leads to the one that is between the Ferrel and high Hadley cells form the high pressure. They form the permanent warm anticyclone. So from the permanent warm anticyclone. Yeah, there. So, and this is usually, it ranges from 20 degrees, say the north or south, yeah, 20 degrees to 45 degrees north or south of latitude, of the latitude, okay? Oh, so we have located where they are, yeah? So let's just finish with the permanent one, yeah? So that's where it's found. So when we have excess here, what did you say happens? When you have this, we don't need the whole lot, just need half of it. Yeah. Okay. So when you have excess air in the upper layers of the atmosphere, that means you have convergence with you at the top, and then the subsidence. What is that? Subsidence. Good. Then at the lower layers, it is going out. But you see, this is on the ground. The ground, you have friction, and you have all those things. So this thing is trying to go out at the same rate that it's coming in, but now it can't, because here it's not as free as on top. So here you have like a jam. There's a jam created here, and you have a lot of cars coming in. So you have a lot of pressure. There's a whole lot of pressure there. So it creates a high pressure region here. Another thing, when a parcel mass of air is forced to descend because of subsidence, it is going to a place, so it's going to a layer where the pressure is high. Up, low pressure, down, very high pressure. Up, low pressure, down, low pressure. So when you're up and something is going to a place of low pressure, that thing is squeezed. So this thing is squeezed, so it becomes smaller here. So when you squeeze something, it gets hot, right? When you squeeze a balloon, when you squeeze a ball, it gets small and it gets hot. Yeah. So when you inflate your tire on the car, it gets hot. Why? Because you're increasing the pressure. So as the air is descending, it hits adiabatically. We'll see what adiabatic hitting is when you get to stability. So just know that when air goes down, it hits adiabatically. So as it hits adiabatically, then the descent forms, it comes maybe as cold air, and then reaching there, it gets hot. So here you have layers of hot air. And here you have cold. So as it descends, you get that, and the hotness is why we have this bug called warm. So it's a permanent one. Why? Because it's a global thing that happens every day and every time season. So it's not something that you can do away with. Yeah. So that's just permanent. And it's found between 20 and 45 degrees. So at this layer, you have what we call it subtropical polar high. Subtropical high pressure. Sorry about that. Subtropical can be tropical polar. Subtropical polar high. So you have that subtropical polar high. Okay. So moving on, we have. So why does it range from 20 to 45? Why can't it be just one location? Because we say this thing is constant throughout the end of time. Till the end of time, it's still there. They move. So why does it change? So it ranges because these cells move periodically. They move either north. The subtropical polar high either moves north or south depending on where the sun is. So if the sun is at the equator, it will be at around 30 degrees north. Yeah, on average, when the sun is at the equator. But when it moves to the north, the subtropical high in there. So remember, we have both of them. There is one there, and there's another one at 30 degrees south. Subtropical high. Thought I rectified this. Subtropical high pressure. It's just corona. Nothing serious. Subtropical high pressure. This is also subtropical high pressure. So we have both of them. So when the sun is at the north, this is the sun. When the sun is at the equator, the two of them are around 30 north and 30 south. When the sun goes north, so that means summer in the northern hemisphere. So the subtropical high will have to move away from it, yeah, because the whole thing is moving north. So it will move to up to 45 degrees north, yeah. Whilst this one is moving, keep maintaining the same distance, it will move up. So in winter in the south, this thing moves out. That's summer in the north. So if the sun is here, both of them are at 30. And the sun goes to the North Pole, the subtropical high in the north will go to 45, and this one will go to roughly 20 north, 20 south. And the opposite is true. When the sun goes to the southern hemisphere, when it's going for Christmas, so this tropical high will go further south to 45 degrees south, and this one will come to 20 degrees north. So that's it. So you need to write that and keep that in mind. And the weather. Now we want to talk about the weather in the permanent warm anticyclone. So how does the weather look like? So you just wrap this because now we're done with it. So in case you need to pause, just pause and write, and then continue with us. So what do you think the weather is? Because this place, now you have a place that looks like this. Warm air, air coming down constantly. This is high pressure. So first of all, this is not good, because for you to even form weather, cloud, water needs to happen, the air needs to go up. But in our scenario, high pressure, warm air is going, well, air is coming down, and as it comes down, the air becomes warm. Yeah? And the reason for the high pressure is air coming in at higher rate than it's leaving out. Yeah, because of temperature or anything. Yeah. So you have that. So it's very hard for you to form any cloud. So the weather, condensation is inhibited. You know that condensation is inhibited, thereby have clear sky. So and worse enough, air, what the reason for inhibiting, another reason is that air is heating vertically, because you know that water vapor needs to cool, but in this case air is heating adiabatically. Okay, so therefore the temperature, the weather becomes, we get hot temperatures, hot and dry. So it's basically hot, dry, and then clear clouds, no clouds, clear sky. Stable weather. So it's just a stable weather. Another thing you need to know that is at night, because you have a clear sky, so you have clear sky on the ground, clear sky here. Now on the ground, the sky is clear. So during the day, this thing was heating up, so the earth obviously warms up, whether it's the ground surface or water body, so it doesn't matter. So it's still the same, because it's clear sky. So ordinarily we usually have a piece of, what do you call it? So when you have clouds here in Nairobi, so when the sun hits the ground at night, because now there's no sun, the earth dissipates heat. There's heat that is relayed from the earth, yeah, the one that it was absorbing during the day. So as it gives away that heat, and it then gives away until it becomes cold itself, yeah. So if you have clouds here. So assuming my hand is the cloud, so when you losing the heat will hit the clouds, will come. So ideally you have a warm, generally a warm atmosphere near the surface. But in a desert or in this scenario, the earth will lose all the heat in a very short time, because now there is nothing that is heating it any further. So it has lost the heat. So now it is colder, it becomes even colder than the atmosphere. So what happens is that it starts heating. This is at night, remember, at night. So it starts cooling the lower layers of the air, the warm air that is there. It starts cooling it, cools it until it becomes very cold and condenses to form what we call a fog. And this is, we refer to it as radiation fog, because it is due to radiation from the earth to this. So during the day, you find that there is a fog. Just after a clear cloudless sky at this point. So we have radiation fog. So examples of such as, so the only visibility will be poor when you're having this. Visibility will be poor, but because even here there is no circulation of air. Yeah. Then here visibility is poor because you have radiation fog at night, developing at night. So it clears maybe by some 10 a.m. there. So yeah, I've been there. Let me not lie, but that's the case. So in water we have examples. So in water we have the places like this that are in the sea. So like islands, we have the Azores, and the Bermuda. The Bermuda. But in land, this is the place where we have, if you consider the 25 degrees north or south to 40 degrees north or south of latitude, that is where we have most major deserts. So major deserts, not deserts, major deserts are located there. Yeah. So major deserts like the which one is this one? Sahara Desert, the Namib Desert. Yeah. So the different types of deserts. So let's look at the cold. Unless there's any question, you can leave it at the comment section. I'll respond to it on the comment section. Comment or so question. So on the cold anticyclone, the same as this one. It's due to excess air at high altitudes, because now you remember we had two high pressure areas on the. I'll just show you. We had two high pressure areas on the global air atmosphere circulation. Yeah. So don't need to show you. We had the feral cell there, the Haley cell, and then we had this other one that came all the way to the north, and the direction of wind was like that. So here we had a high pressure zone. So why didn't we consider this as a permanent warm anticyclone? Because it is not a warm one, it's a cold one, because it's at the pole. Yeah, it's at the pole. So this is one of a type of cold anticyclone, but it's not what is the word? It's not the major one. Yeah, it's not the major one. There are others, we'll see. But it is, yeah, if you say it is, it is. So you can't dispute that, because we have. So what makes it different from this is that if the air converges and then subsides, and then it diverges. It's still the same concept, but the only difference is on the ground. This ground is colder. Yeah, the ground is colder. So on the North Pole, obviously the ground is very cold. Hey, you don't even want to shower. So Corona can't save you there. So at the pole, it's really cold. Yeah. So what happens is that when this thing subsides, when the cell comes down, so it warms adiabatically, but you see this layer is cold, so the earth radiates, cools the surrounding air. So when something is cold, it becomes smaller. When you cool something, it reduces. It is compressed. Yeah, that's the key word. It is compressed. So this layer it subsides, becomes warm, but it is cool. So a layer, this one becomes a layer of cold, and then this cold one successively cools this other one, it successively. So until you have a layer of cold air below and warm air above. Interesting, right? So now what happens is that air will be coming and then it's cooled. So here you have a cold. Here you have cold air. Here you have warm air coming. So it cools the whole thing. So this is very. So here you have this. So when you have this, here you have cold air. So unajiuliza sasa, because you have cold air there. So ordinarily, if you have something that is cold and here you have warm, so what weather pattern will you have? Is this thing stable? First of all, actually it's very stable for that matter, because just try this. Go to the dispenser, take cold water below your cold water first, and then put hot water. You notice that when you drink, it will be warm, and then after a while it will be cold because it's stable. But when you have it the other way around, put warm and then cold, it will mix faster. Yeah, because it is not stable, because the heavier thing will want to go down, the lighter thing will want to remain high. Yeah, so you can't throw a plastic and water and you expect it to go down. Yeah, you can't do that. So that's that. This is the whole thing. So the major difference is that is the land that the air is descending is colder. The cold surface cools the air, as you said, and makes it to further sink, forming the cold anticyclone. So it's examples that in the North Pole, that's one example. We have the Siberia and the North America in winter months. So the North America, so there, over here, and the Siberia here, somewhere there. We have so Siberia and North America in winter months, when the sun is on the southern hemisphere, is when we have this cold anticyclone on top of those places. So apart from that, we also have what you call the temporary anticyclone. So just to mention, the temporary anticyclone, you can write, is a ridge of high pressure found between two polar front depression. It's a ridge of high pressure found between two polar front depressions. So polar front depression, we'll talk about it when we talk about the cyclones. Yeah. So the extensive cyclones, yeah, large extent cyclones. So those are what we call the polar front depression. So polar front depressions are depression of low pressure. So when you have low pressure, you also have places that have high pressure, yeah. So and those places are what you call the cold temporary anticyclone. So let's just as a summary, let's look at precipitation is nil, icing nil, we don't expect either icing. Turbulent is light in both of them. Visibility is poor because you don't have the atmosphere is stable, so visibility is poor. And then it's even worse because in this one we say we have radiation fog developing during the night. So visibility is poor because especially in this one you have what you call, after the subsidence we have cold air and warm air on top. So this is cold, this is hot. So this is another key thing that you should note, that as you go high, temperature becomes warm. The higher you go, the hotter it becomes. So this is an inversion. We expect the higher we go, it should be cooler. But in this case, the higher you go, the hotter it becomes. So this is an inversion, and we call it the subsidence because it is subsidence inversion, subsidence inversion, subsidence inversion. Yeah. Okay. So that's it. So because of that, so this place is stable. We don't have good visibility because the air is not mixing. Yeah. Okay. The only thing that we need to note is the movement of air in high pressure. So just to finish up, I can decide to wrap this one. So how does air move in a high pressure system? So both of them, yeah, it doesn't have to be one. So how does air move? So this is a simple, instead of cramming, you can just visualize it as this. So here you have the equator. So let's say this is our high pressure region. It's our high pressure region. So in a high pressure region, ordinarily air wants to leave. Air leaves from a high pressure to a low pressure. So it wants to leave. It wants to leave, yeah. So, but because of Coriolis force, and Coriolis force emanates from this logic. You don't need to cram it, you just need to understand. So air is moving, if air is moving from this point to this point. So if you have this point, this is the largest point of the orange here. It's the largest, has the largest diameter, this equator. So the earth here, anything that is on the equator is moving at a faster speed than something that is on the pole, because if you rotate something, if I hold a ball here like this, and this thing is moving, the top is not moving at the same speed as the diameter, right? You can see, yeah? This one is just like stagnant. So a wave that is moving at the equator is moving at a high speed. So if you move something from a high speed to a low speed, what happens? If you're in a pickup and you throw an orange outside the pickup, what happens to the orange? It will lag behind. If you're in a matatu and you throw something outside the car, it will lag behind, obviously, because it's going to a place of less speed. So here, if air is moving from the equator to a place, this one is a place of slow speed, it will lag behind because this is the direction of rotation. So it will lag behind, right? So can't come in and already Numa. That's French. Yeah? So if it's moving from here to here, what happens is that it lags behind, and it's moving from here to here in this direction from a low place to sorry, this is not the case. Lagging behind is yeah, it's the case. It's the case because it's moving from a faster place to a slower place. Yeah. So if it's moving from a faster place to a slower place, obviously it will go ahead. It will go ahead. And if it's moving from, so this one will be moving, you look that way. Then this one is moving from a slower place to a faster place, so it will lag behind. So this creates an angle that looks clockwise. Yeah. So in the northern hemisphere for high pressure systems, it's clockwise, and the southern hemisphere is anti-clockwise. So in the southern hemisphere, if you look at this one, it is moving from a place that's slow to a place that's fast. So obviously it will lag behind. And this one is moving from, if you go to this direction, from a place that's fast to a place that is, I'm comparing to the equator, a place that's fast to a place that is slow. So a place that is fast to a place that is slow. So it will go ahead, because we say the direction of rotation is eastwards. So this creates a clockwise, because it will end up going that way. So creating a clockwise movement. This is anti-clockwise. Anti-clockwise. Yeah. So if it goes this way, that is anti-clockwise in the southern hemisphere. So then we have what we call a cone. A cone is not a high or a low. It's a region that is neither high pressure or a low pressure system. It's either between two lows or two highs. And there the isobars are widely spaced, with winds being light and very variable. Yeah. So in the summer we expect in the colds, in the summer we expect thunderstorms and fog in winter. So that brings us to the end of the lessons. Yeah, in case of any questions, just drop it on the comment section. So, and remember to subscribe. It's been nice. So I'll just the part 2 of this video will have the low pressure system. Hope you enjoy it. Ciao.